Okay, hi MATH7502. Can somebody give me a ping if you can hear me? Yes, thanks. All right, thank you. Let me join also on the iPad. Let's do this. One sec. All right. All right. Hi, everybody. It's 5 in the evening here in Brisbane. Those of you overseas, give me some times, locations and times. So just so we kind of see where and what, put it in the chat or say. So who's not in 5 p.m.? Somehow I cannot see the chat. Sorry, I'm still with a bit of Zoom growing pains. So who's not in it? Whose time is it not 5 p.m.? Anybody is not in 5 p.m.? I'm sure there are. On the Chinese Eastern Seaboard, it's 5 p.m. as well. No, it's 3 p.m. in Manila. Hi, Beatrice. And 3 p.m. for Mengfei and 3 in China. Okay, Wang, thanks. 3 p.m. Is all of China one time zone? I doubt that, right? Probably multiple time zones in China, like 3. How many time zones are in China? 1 time zone. Really? I didn't know this. Okay, that's good to know. So only 1. So I learned something already. Are there any questions before we start? No? So I assume everybody has Julia, Jupyter running, not necessarily now, but that you have Julia and Jupyter on your platform. If anybody is still having serious difficulties with Julia and Jupyter, please feel free to reach out to me. I'll help you install this. I know sometimes it's a bit of a rocky road, but it shouldn't really be. So just write me an email afterwards, and we'll close it, because you do need Julia and Jupyter running. There was also a question, I think, by Fadi just before an hour or two on Piazza. Do you want to ask it now? Yeah, go ahead, Fadi. We might as well ask it now, just because it's so close to the lecture, and we'll start then. Or you can digest it and think about it if you want. All right. So There's a question about the schedule for the content. Well, that's kind of very organized here. Well, sort of organized. You see now, you see my Chrome, right? Can you guys see my Chrome window? Somehow I don't have feedback on you seeing my Chrome window. No, I see now on the iPad that you can see the Chrome window. So there isn't an exact kind of schedule for what are we doing in each specific lecture, but the assessment is what is gonna guide you. So specifically, for example, this is a course website, obviously, right? This is Blackboard, okay? So specifically 2 weeks from now, minus 3 minutes, you're gonna do quiz 1, okay? That's not so far, quiz 1. So you might be thinking, what's in quiz 1? So then you can click here, quiz 1. Well, you might have looked at this earlier, but I just put it today. I'll answer your question in a second. Fabi, and same for your question, Junan. So quiz 1 is, here's information. So basically you do the quiz by yourself for 70 minutes, plus you got another 20 minutes of grace period to kind of scan. Okay, so the quiz and nothing in the quiz. So no, often I actually leave open material, but now this is a quiz. The quiz is rather basic. So no book, no friend, no calculator, no mother, no father, no brother, no sister, no son, no daughter, only pets. And you do the quiz. And then you take photos and you scan it and you upload. All the instructions on how to scan and upload are here, okay? And you send a voice recording, like the beautiful voice recordings I got from almost all of you. If somebody still didn't send me their voice recording that just says who you are, please send it. I listened to him once and I'll actually listen again, and then I'll little by little get to know you. So what's in quiz 1? All this stuff, okay? Now, quizzes are basically just meant to see basic knowledge, okay? So they're kind of checkpoints for you. This course doesn't have a final exam, right? So the quiz is like a checkpoint for you to see that you're kind of up to date with the basic, slightly more boring things we're doing, just a whole bunch of linear algebra. I say boring because the quiz is not going to be exciting from a data science perspective. I mean, come on, it's 70 minutes. So that's quiz 1, okay? So that's in 2 weeks. And then you've got, you might be asking how to study for quiz 1. So you study for quiz 1 by doing assignment 1. Assignment 1 will be updated tomorrow or the next day, okay? So that's assignment 1. Plus I can give a few more review exercises. I'll send them in Blackboard, okay? So for those of you that have done linear algebra to some level, it shouldn't be a whole lot. For those of you that are making up stuff, specifically those that are kind of picking up here, on the background material, I know there's a few of those. Quiz 1, you know, you need to kind of get rocking, because in 2 weeks you kind of want to make all this backup, all the kind of backlog, all the background, and then get on with quiz 1. Right? Okay. Questions about that? Please don't hesitate. By the way, voice is fine if you want to ask with voice. But this is recorded and then given. Now the final project. So here's the final project. So I click the final project. Oh, proctor you? No proctor for the quiz. No. You need honesty, and you also make a voice recording in the quiz. No proctor you. Okay. So you write it down basically and take photos. Okay. Where did you use proctor you, Rob? Or maybe you just have heard about it. I mean, I think it's not, our school doesn't really use it. Final exam, oh, maybe something in ITEE. Could that be? Okay. School of Maths and Physics hasn't used the proct. So the final project is submitted individually, okay? Okay, just digression again. Do we need to use Julia in the quiz? No, you actually cannot, okay? So the instructions for the quiz is like mimicking a class quiz. So this is how I do it in most years. Quizzes, you come to class, everybody's timid, timid, something like that, very tight, and you sit for 70 minutes by yourself. Cannot use any written material, cannot use internet material, cannot communicate with others, cannot use software. cannot use anything else. You can just use an A4 double-sided A4 sheet, which you then need to upload. And preparing that sheet is obviously good practice, and a scientific calculator. Okay, if you don't have a physical scientific calculator, you can use a scientific calculator app, but it needs to be a basic scientific calculator, not something that can do fancy things. This one took the final exam for last semester, not good experience. Sorry about that. Was this MATH7501? This one? Was this MATH7501? Not. No. Okay. Some of you did the MATH7501 quiz last semester, final exam last semester. There's not a final exam in this course. Back to the final project, right? So the final, oh, you mean the ProctorU, gotcha. Okay, no, we don't do ProctorU. No need to speak about ProctorU anymore. ProctorU banned from this course. All right, so now, until maybe next year, I don't know. So don't do it next year. Math 7, the final project, now this is kind of, I want to get back to this. For the final project, it's individually. Somebody just asked me, yes, it's individually, but you can have up to 2 named advisors. What's a named advisor? And you must have at least one, okay? So an advisor, again, is somebody in the course that's giving you advice. What are they doing? They are actually, she or he or that person is giving you advice. They are actually telling you, oh, this looks good, this doesn't look good, this looks good, this doesn't look good. That's what the advisor do. They're kind of helpers, but it's not their projects, okay? I'll give more information about this, but basically you need to now offer yourself, and I'll help you guys kind of mix and match, especially, unfortunately, most of us cannot meet physically, some of us, so you need to do this virtually. So you'll be offering your services as an advisor, and others will be advising to you. So you basically can get their advice. What's your advice or feedback on improving the quality of your project? Now, one of the reasons that I did this, and this is important, I've been speaking to quite a few of you in the last couple of days, also to other students from the Master of Data Science program, is there are different attributes of students. So I've seen some students, also international students with exceptional English skills, but those students perhaps say that they haven't done a whole lot of math and a whole lot of programming. There are students that have great programming skills, but the mathematics is a bit rusty, or maybe the English language and presentation is a bit rusty. And of course, there are students that have maybe done a whole lot of math, or have done a considerable amount of math in your engineering degree or something like this, but programming in English is rusty. So your best strategy is actually to get advisors, not just for this final project in general, that complement your abilities. Okay, of course there are super people that kind of are good in anything, and there's also people that suck at everything, but you'll improve them. Whoever you are, try to get people that help you. Okay, so that's for the final project. Now, what's a project about? In the project, you basically make 3 demonstrations, and there'll be detailed instructions, okay, about 3 out of these 6 topics. You pick these 3 from from data science use cases, of which today we'll be speaking about clustering already. Okay, so there are 12 use cases here. We'll speak about them actually more today. And you pick 3 of these and you make demonstrations. I'll explain, and of course give instructions how. Okay, you can look at the projects from last year to kind of get a feel. It won't be exactly the same, but it's basically, it's exploring the subject, it's giving some examples, it's giving an explanation, and you're basically going to create a stylized Jupyter notebook, etc., and a video. So you're actually going to create a YouTube video, okay? That is kind of the essence of the project. The exact instructions, way down the road, week 9. That's all I can say so far about the project, but that's roughly how it is. Are there any questions about that? No? Okay. So let's get back to the material. Let me start Jupyter. Oh yeah, and there was, I think, a technical question by Fadi. So the question was, now Fadi, if you don't mind me asking, are you still in quarantine? This is on video. Yes, okay, well, my heart is with you, hang in there. I assume it's not too long. Okay, probably not, right? Okay, so this is the Jupyter Notebooks, data science use cases, no. Anybody else in quarantine here, by the way? I mean, we're all in some sort of quarantine, but in kind of real quarantine? Like closed in a COVID hotel or anything like that? No? Okay. What times we live in. Okay, so I'm starting this Jupyter Notebook. I don't know why it's not starting. It should any second. And that's the same unit we worked on. And there's a bit of updates to this and also in GitHub. Now, of course, I keep pushing to GitHub. So the way you can do this is when you go to the courses GitHub. Okay, you go to the courses GitHub repo. So you can, this is the courses GitHub repo. You can also get a history of these things. So for example, if you click history here, you see previous commits, so you can get older things if you'd like, but there's no real reason to. One thing I noticed that some people did, I'll just say it right now, so I know this is maybe a basic thing. So if I click this notebook and I do right click and I do save link as, what's it going to do? It's going to save the HTML file, which is this one, which shows me this file. Okay, so that's not what you want to do. What you want to do is you want to right click, or on my Mac I do a double tap, and whenever I do save link on this download, you probably worked that out. Okay, so that's in GitHub. I'll close GitHub. And let's, oh, and I close screen sharing. Sorry about that. Sorry. Un momento. All right. So we were roughly, oh, and now to Fadi's question. So Fadi's question was, what's the difference between I'll answer it here. Let's just get back here to roughly where I was. I think this is where we stopped, roughly, yeah. So Fadi's question was, what's the difference between something like this for a vector and something like this for a vector? Okay, let me put this also. So it kind of matters. We use those vertical lines, those pipes, often in mathematics. Now here, this top thing, this is a norm, okay? And what norm is it? If we don't specify, it is the 2 norm, right? It's a L2 norm, okay? It's the sum of the square of the elements, the square root of that. It's a Euclidean norm. This thing is actually not really defined if V is a vector. If V is a scalar, it's absolute value. Okay, that's what we mean by that. Or if V is a complex number, it's a magnitude, right? It's the real part squared plus the imaginary part squared, the square of that. But if V is a vector, we don't really have meaning for that. But of course, we're going to seriously overload this notation because we'll also put those 2 bars sometimes to mean the determinant, okay? But then this V has to be a square matrix. We'll get to that soon. And what about if V was a set? What is this? What are these kind of, what do we mean when we put these 2 pipes around the set? You know, the size of the set, yeah, the cardinality. Coordination, that's a nice word. Cardinality of the set, right? The size, like how many elements are in the set. Okay, but for a vector, this is not really common to say the absolute value of vectors. There's no meaning to that. Okay, all right. Next thing, matrix multiplication is associative. All right, so here's a simple example. So let's get 3 matrices, A and B and C. Okay, no problem. So when I do here, I'm choosing just a matrix with entries 10 and 20. Let me just go below and let me add here display A, and display B, and display C. So this is just a way to get matrices with just entries that are either 10 or 20. So that's a 2 by 4 matrix. And then you've got a 4 by 5 matrix. That's your matrix B. And then you've got a 5 by 3 matrix. Look, the dimensions match. 2 by 4, 4 by 4. This 4 that matches this 4, so we can actually multiply. And this 5 matches this 5, so we can multiply. So we could speak about A times B times C. However, we didn't really define what a matrix multiplication of three-way matrix multiplication is. We only had two-way. And when you see such a definition, what you are implicitly assuming is that there's actually the associative rule, which means that you can either treat it this way or A times B times C, and the multiplication would be the same. Okay, and if you want to prove this, you just need to look at kind of how matrix multiplication works, and that works. Now, when you do this in Jupyter, it's going to do it left to right, okay? But the point is that it doesn't matter where the brackets are, so when you carry out this multiplication, you get this as a result of multiplication, and of course, if you did A times B times C, it's like A times B times C, okay? That's the associative rule. Is matrix multiplication commutative? Commutative? Is matrix multiplication commutative? Commutative. Addition is commutative of numbers, multiplication of scalars are commutative, but matrix multiplication is not commutative. Okay? So take two matrices, we might have done this already before, and they generally will, you cannot do A times B is not B times A. I won't write it because I think we did that before. Okay? You can do, there are certain matrices that commute, but then they're called said to commute. Okay. So the identity matrix, okay? Now, the identity matrix, you can view in two different ways, okay? You can view it as, and I think I asked you guys to watch the 3 blue, 1 brown video of a linear transformation, right? So let's see, I recommended, I think, I'm guessing that this is the first, to see that, to view a matrix as a linear transformation, oh yeah, linear combinations, okay, you watched that, and I hope you did, and you watched that. I mean, these videos are just beautiful. Let's see, so what's this one about? In addition to having nice music, it's linear transformations. Okay, so we're still not getting to that formally in the lecture, but you can already view a matrix as a linear transformation. We'll speak about it a bit more actually next week. Okay, so the identity matrix is the identity transformation. It's a matrix that if you multiply it by another matrix, you don't do anything to the other matrix. Okay, it doesn't change anything. If you multiply to a vector, you don't change anything to that vector, etc. Now, in Julia, you can actually do, just after you've included the linear algebra package or use the linear algebra package, you can just write I, okay? And that's actually, it's like an identity matrix that's, in general, it has a type, uniform scaling, and you don't have to worry about its type, okay? So you can do operations with it, and Julia will be smart enough to do that, generally. We'll see it work. Okay, let's see that work. Let's define a matrix A. So we've got a 2 by 2 matrix. So we're going to multiply the matrix A times I, and what I'm doing here is I'm going to ask, does this thing equal A? Before that, I'll just open above. I'll do A times I, and let's see that that didn't change A. Okay, no surprise. But if I want to kind of verify that, I can say, does that equal? So equal is the comparison operator, and this guy does it element-wise. Okay. So is every element of this an element of that? And yes, and it's all true. Okay, so that's fine. And of course, left multiplication does the same, also doesn't change the matrix. Okay, identity. Okay. Now, let's say I didn't want just an I, which is kind of an arbitrary abstract thing. I mean, the nice thing about this I, it doesn't take any space in memory. Okay, let's say I actually wanted like a diagonal matrix. Well, I can use for example, the diagonal function, okay, and stick in a vector here. So if I do this, I do a vector ones of 2, I get a vector of 2 ones, okay, or I can do ones of 3, it's an array of 3 ones, etc. Okay, so if I do diagonal of some vector, in this case it'll be ones of 2, I'm going to get a diagonal matrix. But Julia again remembers, it's not the core part of the course, but Julia again remembers that its type is a diagonal. So it prints it like that. It doesn't actually, you know, I can do diagonal of 100, right? It didn't allocate here 10,000 locations in memory. It just remembers those 100 elements of the diagonal. Okay. Now you see this capital. Why is this diagonal capital? Somebody from software engineering kind of take a wild guess. Again, this is not about linear algebra. This is about Julia. So it's just a convention, right? So we've already seen that we have like exclamation mark at the end of a function is a convention that says that this function actually mutates its argument. And Rob is taking a wild guess that it's a class. Yeah. Well, there aren't classes in Julia, but it's the constructor for the diagonal struct. So that's a common thing. Okay, so you can create a struct. So constructors are typically first letter cap. And indeed, the types or the class, it's like a class, it's a type that is also first letter struct. Okay, that's a common convention. Okay, so yeah, your answer is as close as it could be. Okay, you could still do a question mark on diagonal and you know, see the help for this function diagonal, which construct a matrix. Okay, blah blah blah. Okay, just because we're speaking about this is kind of so more function, I guess. No, it's not. Well, diagonal a construction. Well, in general, in Java, in C++, etc. A constructor is a function that creates a class. Here it's a function that creates a struct. Okay, and a struct is kind of a class. It's just that in Julia, the structs don't have methods, so it's not really object-oriented. Yeah, in C# as well, as Martin says. All right, so I mean, in kind of, yeah. Those of you that haven't done this type of software engineering, don't worry about what we're saying now in seriously, because this is not kind of the core part of the course. In general, Julia is a calculator for the course, not much more. So I'll spend less and less time on it as time moves. This function diag, just so you see, so this is our matrix, my I, right? And diag is the opposite. And sometimes you want to do this mathematically. You want to retrieve the diagonal elements of my I. Okay, let me just create another matrix just so let's just see this. Might as well close this thing. So let's create the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Very creative matrix here. Okay, so let's do diag of A. Okay, so we're going to get 159. And let's do the sum of the diagonal of A. So it's going to be 1 plus 5 plus 9. I'm just putting in comment. Okay. There's something in linear algebra called a trace, and you're going to do a whole bunch of linear algebra things this Thursday with Sam and Walla. So the trace of a matrix, trace of a matrix, of a square matrix, is the sum of the diagonals. And that actually plays a role. We'll see that that's an important property of the matrix. Okay, so the sum of the diag of A is like the trace of A. Okay. You can also, if you want to construct different things, so this is kind of construct a, let's call this a banded matrix. The word band is like the band, something going kind of diagonally. So construct a banded matrix. So this 2, it says position 2, put a 5 and a 7. Okay. So that will construct, it moves, this would be, if I put 0, 5, 7, it'll put on the diagonal 5, 7. Okay, but it doesn't actually create a diagonal matrix. It actually creates a full matrix. If I put 1, 5, 7, it'll put kind of in 1, 5, 7. I can also put, say, -1, 2, 3, 4. You see, it put in offset 1 at 5, 5, 7, and offset -1 it put 2, 3, 4, like -1 going here. So this is how you can create banded matrices. Okay. So a lot of what you need to do sometimes is just to kind of create the right matrices. So you've got these tools for you. This type of thing in Julia is called a pair. Okay. Questions? No. All right. So we're getting kind of to the next thing, and this is kind of a hybrid between a review and just exploring other things. Inverses. Okay. So here goes. Given a square matrix A, its inverse is a matrix, and we denote this matrix like that, A to the power -1, as you would like inverse, like reciprocal, okay? Such that when you multiply A by its inverse, you get the identity, okay? And also when you multiply A by its inverse, you get the identity. Okay, so that's like an n by n matrix. That's an n by n matrix. Identity is an n by n matrix. Okay. Now we'll soon prove that if you have a left inverse and the matrices are square, then the right inverse must be the same. So you can't have like a different right inverse and a different left inverse. In general, this thing I'm highlighting now, this blue thing that's highlighted in blue, is called a left inverse. And this is called a right inverse. So some matrices, even non-square ones, have a right inverse but not a left inverse. Some have a left inverse and not a right inverse. An inverse is both a left inverse and a right inverse. We'll get to speak about this more when we get to a much more advanced concept, which is the pseudo-inverse, which is a specific left inverse. It can also be viewed as a right inverse. Okay, so that's the inverse matrix. You never write like that. Some of you, I hope, have already started to do some basic LaTeX like this LaTeX I'm doing here. So you never write 1 on a matrix, okay? Okay, this looks like an inverse, right? So that's just, you don't write it, okay? You don't write this. One of the reasons you don't write this is, for example, if you had like some other matrix here, you know, let's say that B is a matrix and I'm writing B divided by A. Do I mean B inverse A or A times B inverse? Never write. Okay, so you see, when I write this B over A, you don't know if I mean like a B O, if I'm left multiplying by the inverse of B or I'm right multiplying by the inverse of B, right? And you agreed with me that matrix multiplication is not commutative. So it's also when you multiply by the inverse, multiplying by the left is not necessarily multiplying by the right, okay? No, no, right? But so we do A -1. Of course, with numbers you can, because left multiplication by a scalar is like right multiplication by a scalar. Okay, so if A is a scalar, it's a number, you can't do 1 on A. Well, you can't do it for all A's, right? Don't divide by 0, not good. Okay. Okay. Okay, Julia didn't mind so much, it gave us infinity, but why is it not negative infinity? I don't know. Okay. Right? I mean, why is 1 on 0 infinity? I mean, maybe we meant going for the left and it's actually negative infinity, right? Because if you're telling me that 1 on 0 is like 1 on x, if you take x smaller and smaller and smaller and smaller, this thing indeed goes to infinity. But if you took x from the left and you made it -1, -1/2, -1/4, -1/8, -1/16, etc., it's actually going to be negative infinity. Julia decided it's infinity, but mathematically don't do it. Okay, that's infinity, inf, which has some uses as a number. It's not mathematically a number, but it's a number in the number system of the computer. Everything okay? Yes? Okay. I'm guessing that silence is okay. Sometimes when you Zoom lecture, after a while you think, thank you, Jonathan, I'm just saying good. Yankee. So sometimes when you Zoom lecture, you kind of, after a while, you feel you're speaking to yourself. Also happens when you speak to people face to face, by the way. All right, so AI, let's call this the inverse of A. So guess what the function inv does? It gets the inverse of A. But here we have the wrong A. Let me choose some nice A. We'll get to the singular exception in a second. Okay, let's make A 1, 2, 3, 4. Okay, so the inverse of A is going to be this guy. Let's check. AI times A. What does it give us? What is this matrix? What's this matrix I'm highlighting? It's, thank you, it's identity, and numerically it's, yes, it's identity. This is kind of a numeric zero, right? I mean, it's kind of non-zero, but these numbers are 64-bit, okay? And you know, it has a bit of noise and it's kind of almost zero. E to the minus 16, small enough it's a zero. Let's multiply it by the right. We get, well, did I do this? Yeah, the same thing, slightly different number because of numerical error. Okay, but that's identity. Okay, so no surprise there. Now this function in, which you get from the linear algebra package, the linear algebra is a built-in package, is not actually a function that you often use. So you use it a lot in this course, but when you're doing real data science, real mathematics, you rarely really compute the inverse of a matrix. It's inverse of a matrix is something you need more kind of symbolically. You do it a bit, but it's not to actually really do numerical mathematics. You don't compute the inverse. Okay. So here's a claim. By claim, I mean like theorem, proof, proposition. Okay, one of those, something that has a mathematical proof. Okay, it's just whatever we call it. It's a claim. So if B times A is identity and A times C is identity, then B equals C. The way I can read this is, if B is a left inverse of A and C is a right inverse of A, then B must equal C. Okay. So this claim says that, you know, that when we define here the inverse and we said, well, you multiplied by the left, when we did it here, you multiplied by the left, you multiplied by the right, it's going to be the same inverse. You can't get two different inverses. You can't get a left inverse to be different than the right inverse. Okay, so if there's a left inverse and there's a right inverse, they both must be the same thing, and that's what you call the inverse. Okay, that's this claim. So let's prove that. Oh, let me share this other writing device. Okay. So yeah, that works. We have a claim. If BA is I and AC is I, then, this is how you kind of write then, this thing, okay? Then B equals C, okay? And I'm gonna write here like in red, you know, they're both A inverse, and that's what you call A inverse, okay? But we're never writing inverse when we're actually proving this claim, okay? Proof. Okay, so let's look at B times A times C. Okay, Now, matrix multiplication is associative. So I can write that as B times A times C. Okay. But what's AC? What's AC? I can't see the chat now. What's AC? It's I. Okay. So that's, I'll just put an I here, like an I on green. Okay. And what's BA? I. There's a lot of I's in the chat, like I. You guys are very self-centered. I. Okay. Also I. Okay, fair enough. Thank you. I'll put an also I. Okay. So then we see that B equals C, because B times I is I times, B times I is B, because this is B. And this is C. Okay. So then B equals C. All right. That's all. End of proof. Not difficult. But actually, when you, not difficult once you see it. There are a few of these linear algebra proofs that once you see them, they're not difficult. But if you don't see it and you try to kind of challenge yourself, and not immediate. Not immediate. Any questions? No. Okay. So since I learned from you guys about the fact that China has a single time zone, so for those of you that don't know, in Australia, then Queensland actually is also, of course, one time zone. Queensland is not too big. I mean, not too many people live west of here anyway. But the Queensland time zone doesn't move. So Victoria, the state below, the guys that are in quarantine now, and we thank them for that. And New South Wales, they have kind of summertime, wintertime. Now we're on the same clock with them, but in Queensland, we don't move the clock. So we're a bit closer to the equator, and especially North Queensland are very close to the equator, so there's not so much summer-winter variation. I think it's been an issue of political debate. So some people wanted to move the clock. I would love it if they do. Is anybody active on this front? No. Okay. Back to business. We got 10 minutes. We're going to do good breaks today. So claim. If A and B are invertible, then so is A times B, and the inverse is AB inverse. You flip the B and the A. Okay? Flip the B and the A. Let's actually go back to the visualize the other one and try to prove that. I think I'm going a bit slow today, but that's okay. Sorry about that if any of you are suffering from the slowness. Okay. So A, B inverse, we are saying that that is B inverse times A inverse. Okay. So what does AB inverse mean? AB inverse means it's a AB inverse times AB. What does that need to be? What does AB inverse times AB need to be? Looking at the chat. I, again, I. Okay, fair enough. I. Okay, so that needs to be I. Okay, that needs to be I. So let's see, if we put here a B inverse times an A inverse, and then we've got that A and B from above, what's A inverse times A? Somebody in Zoom will think that we have a problem with Zoom. It's just caught on I, so I's. Okay, so then this is kind of fun. This happens a lot in linear algebra. Then you have a B inverse times B, and what's that? That's again an I. Okay. All right. So I equals I. All right. So that's how you see that the inverse is flipped. Okay. Back to the laptop. Okay, seems to kind of work. Okay, let's just see this very quickly. Here's A, 1, 2, 3, 4, and B, 5, 6, 7, 8. The inv of the product AB happens to be this. And if I do inv B times inv A, I get the same thing, okay? What we have here in Julia is clearly not a proof, but it's a demonstration. And we'll have to be very lucky that inv A times inv B will be that. And this is something different, unless we're bloody lucky, okay? Because the two inverses don't commute. So you see, this is not the way you do inverse. So you do this flip. And by induction or recursion, if you do A, B, C, you'd flip tut, 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 okay? You'd flip the whole thing. Okay, said no. So if you do kind of multiple multiplications. Okay, transpose. For transpose, let me first just construct this matrix. So the way I'm constructing this matrix is I'm saying I'm going to run on I 1, 2, 3 and J 1, 2, 3. Okay, so I is column, I is rows, and J is cols. Okay, this is a comprehension. Okay, and the ijth entry will be J plus 3 times I minus 1. So this is my way of making a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, okay. That's so I'll put kind of the general formula for ij like that. Okay, so the 1, 2, 3, the j is kind of indexing all the time, adding, and I have here I minus 1 because in the first row I is 1, so I don't want to add a 3. Let's just see for the fun with Julia that I can do this in a different way. I could have done collect 1 to 9. Okay, so 1 to 9, if I just do 1 to 9, it's not an array. It's the type of this thing is like a range. Okay, it's just something that remembers what it's a unit range. It's this object that just says I'm going from 1 to 9 in steps of 1. Of course, I could have gone in like steps of half. Okay, and that would be slightly different. But okay, that I'm just going 1 to 9. Now, collect actually takes this iterable object, in this case this range, and actually gives me the vector 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I think let's try our luck with this function called reshape. Has anybody ever seen reshape in MATLAB? If you've used MATLAB, you've probably seen reshape. So I'll do reshape collect 1 to 9. Maybe I don't even need the collect. I don't know, 3 by 3. Let's see if this thing works. Nah, that didn't work. Okay. But if I do the transpose of that, which is what we wanted to see, then it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is a different, so reshape is a useful function. Look at reshape. There's also, by the way, there's a function called vec, completely not related, but important, because often we more often than you'd think, you actually take all kinds of matrices and you vectorize them. So look at vec of 1, 2, 3, 4, 5, 6, for example. Okay, so this is a 2 by 3 matrix, and we've done vec, and you get the vector from it. It's actually very important because often when you do images and things like that, they're matrices, but you want to treat them as vectors. Okay, and I'm sure that vec has a way to do it. Oh, look, I think, you see, it didn't do it the way we wanted. It went 1, 4, it went from the 1 to the 4, and then the 2 to the 5. So you could look at help of vec. And there's probably a flag that's called like, there isn't. Okay. So I guess the only way to do what I wanted would be the vec of this transpose. Okay. 1, 2, 3, 4, 5, 6. So I've had to use now transpose twice. I've had to use transpose with vec and with reshape, and I still haven't yet told you what transpose is, but you know from your previous reading that transpose simply flips the ij's entry of the matrix. Okay, so back to our matrix A. The matrix A was this, and A transpose, you see 1, 2, 3. This 2, for example, this 2 here went here. Okay. Now look that in Julia it actually changed the type, and the word adjoint means conjugate transpose. We are not going to work with complex matrices in this course. If you do physics, for example, quantum physics, all the time you need complex matrices. Also, if you do some branches of electrical engineering. So matrices, that the entries are complex numbers, okay? We will work with complex numbers because we'll have to compute eigenvalues, and sometimes associated eigenvectors also complex. But generally, we won't work with complex matrices. Now, the adjoint is just like a transpose, but it also does for entries a conjugate transpose. So just so we see that, even though we won't do it, so why not? So here's a matrix with complex numbers, 1 plus 2n, 2 minus 3m. And those of you that are kind of reviewing the math, you might be freaking out now. What are complex numbers, etc.? Do you need them? Well, you need them a bit. You need them for roots of polynomials. We'll need that because these are eigenvectors. So that's, and let's say negative m and 0. Let's see if this works. Okay, so this is now an array of complex numbers. So let me now do A transposed. So look, you see what happened to this 2 minus 3i? This is 2 minus 3i. It became a 2 plus 3i. That's a complex conjugate, okay? It takes a number and it flips it over the real axis in the complex plane. And this 1 plus 2 became a 1 minus 2. Of course, if the matrix was real, then all these, yeah, the matrix was real. For example, let me just take the apply real on A. Just like that maybe. Okay, maybe like that. Okay, so I'm just getting the real entries, that 1 and the 2 and these zeros. So of course, doing complex conjugation doesn't matter. But all I want to, I showed you this also because this word here happens when you do a transpose. What Julia says, it changed the type to an adjoint. So it didn't actually take things and flip them in memory. It just says, oh, I now have the adjoint, which is like the transpose. And if it happens to be complex, then I'll take the complex conjugate. A lot of words for transpose. You saw transpose is going to be simple. What's transpose? Transpose, just before we finish. So let's just go back here to this nice A. 1, 2, 3. 4, 5, 6, 7, 8, 9. A transpose transpose, of course, puts us back in A. Okay. We got a minute. Any question before the 10-minute break? The mandatory 10-minute break. No? Okay, so let's start in 10 minutes. I'll be on like 4 minutes before to answer questions, but 10-minute break. So we start in the next round hour. Okay. See ya. Okay, I'm back for questions, but I'll only start in 5 minutes. So first, Xinhuan, I don't know if you're there, Xinhuan, or you're on a break. So do we have proof in the exam? Do you have proofs in the exam? So there won't be proofs of the kind of prove Cauchy-Schwarz or prove that if a matrix has a left inverse and a right inverse and both things. There won't be these standard things. And there's actually no exam. There's only quizzes, right? So there won't be kind of, it might be, you know, argue why or maybe prove why something very specific, but not the classic proofs. Okay, so, but still kind of these proofs are sometimes useful because going through the practice of understanding them improves your linear algebra. I hope that helps. Yeah, great. Okay, you're there. Now, how to type A transpose in Julia like that? Okay, so that was answered. So you put a little dash. There might be a few of these different little dash, or you can't do that. So you can't do a. So that won't work, will it? No, no. You do this. In LaTeX, I make this a markdown cell. In LaTeX, I do this. Okay. Like mathematical here. There might be a few different characters for that single quote. More questions? No? Oh, Jonathan's asking for a good starting point for learning LaTeX. Yeah, I had it last year, and I'll send a LaTeX. I'll put for myself to upload a LaTeX cheat sheet. So there's two levels of. I mean, if you okay, so just so you guys know. So for example, a student, I today met a second-year data science student that's doing the project with me. And since her project is rather mathematical, I recommended, please do the whole write-up in LaTeX. Okay, so I mean, I write my research papers in LaTeX, my books in LaTeX, etc. So, you know, LaTeX is a great formatting system because even though it's not what you see is what you get, you kind of get this very clean working environment. Now in Jupyter here, you don't need much more LaTeX with the exception of just formulas. So I'll put you a formula cheat sheet. Okay. Today, the really cool people, of which I'm not, I should be, I wish I was cool, working, maybe I am a bit, I don't know, work in Overleaf. So this is kind of a LaTeX environment that you don't need to install. Okay, Overleaf. Okay, so I'll put it in chat. So Overleaf. It's not an intro, etc. But the web is full of them. But I'll just put a formula cheat sheet that you know, so it's like one specific formula. Other things? No, God forbid, no. LaTeX within MS Word, no. MS Word in general is just a name, not good. So, no. So, if you want to see, might as well. Let's share desktop. Okay, so I'm on a Mac here, so I use TechShop. I mean, there's plenty of kind of LaTeX environments. Okay, and let's go here, TechShop. You can see my, yeah. Okay, so this is my draft book. This is what the LaTeX source looks like on the left. So, you know, like this formula here, I'll click here, you know, I write here and I use these commands, subsection and things like that, and it makes a subsection, etc. It automatically numbers the formulas, etc. This is what the LaTeX editor looks like. Okay, and this here is the source. Of course, it's not what you see is what you get. So you got this slight delay between every time I make a change, I recompile to see it appear here. But it really does beautiful typesetting. That's a norm. Now, yeah, okay, so if you have a Mac, you can use textual. Now, on a Mac, actually, what is Keynote? So if you have a Mac, you might use the Keynote to create presentations. You can put LaTeX formulas in Keynote, okay? There might be a LaTeX plugin for PowerPoint, but typically there's this equation editor, which just looks like, not so nice. Okay, but so for example, Keynote has this. The disjoint matrix, you mean the joint matrix in the question? Okay, so in the question, the adjoint matrix. So the adjoint matrix, I'll write it here. Let A be a matrix with generally complex entries. When I say generally, maybe they're just real, but maybe they can be complex. Then the adjoint, and it's sometimes denoted in texts as a dagger. Let's see if this works. A dag? No, a dagger. Yeah, sometimes dagger like this, kind of this thing that the Romans used for crucifixion. So a dagger, this symbol, okay, that's a dagger. So the adjoint a dagger has ij entry, which is overline aj. I'll explain one minute, where overline z is the complex conjugate of z. That is, if z equals a plus bi, then overline z equals a minus bi. Hope that works. Let's see. Okay, so if A is a matrix and it has complex entries, okay, so the adjoint is another matrix, and the ijth entry of this, look, it has aji. You see, I flipped the row and the column. Okay, that's in general transpose, but I also did this complex conjugate. Complex conjugate, sometimes you put a bar above, depending on the, sometimes you put a little star. So you actually did the complex conjugate. So the complex conjugate of z changes the value of the imaginary part to its negative. Okay, that's the adjoint matrix. So again, we won't use it really. Okay, so a matrix is symmetric if A transposed equals A. Okay, can a non-square matrix be symmetric? Can a non-square matrix be symmetric? I'm giving you a thin matrix or a fat matrix. Can it be symmetric? No, because the dimensions, it becomes, if you take a transpose of a thin, it becomes a fat. You take a transpose of a fat, it becomes a thin, okay? Of course, you have square, so only square matrices can be symmetric, but many square matrices are not symmetric. So I don't know what the A, which we currently have in memory, is. This guy, is it symmetric? This is a question. So you'll find many functions like that. It's not symmetric, okay? You can symmetrize a matrix. You can, this is called symmetrizing a matrix. This is kind of slang, symmetrizing. Maybe I'm misspelling it, a matrix, okay? So what you do is you take A transpose plus A and divide by 2, okay? So you're going to, now this matrix is symmetric. Just to see that this matrix is symmetric without thinking about it, we need another transpose rule here. So A plus B transposed, let me put this in a formula. I hope you guys don't mind a bit of LaTeX light, so you already see a bit of kind of LaTeX, is A transpose plus B transpose. Okay. So when you do transpose on matrix addition, then you just transpose the individual entries. So here you see, so then to check that this guy, no matter what A is symmetric, so do a transpose of this, so it's the same thing, because matrix addition is commutative and you divide by 2. This is called symmetrizing a matrix. Why do we do this divide by 2? What if I symmetrize the symmetric matrix? Okay, so see, I've taken the matrix A, which wasn't symmetric. I've created the matrix S, which is its symmetrized version, and it's true. What if I symmetrize the asymmetric matrix? Yeah, so what I'm saying is say B is symmetric, and I do C equals B transposed. What is a matrix C? Okay, that's symmetrizing. Okay, I've taken, B was symmetric, but I also symmetrized it. What is a matrix C? What does matrix C equal? So B was some symmetric matrix. It's B. It's B, as Robert says. So C equals B, right? As several you say, right? Because of actually, you can just look entry-wise, because B transpose, the ijth entry is like the jth entry, and I'm just putting two of the same entry and dividing by two. So I'm taking the average. This is like the average of those two entries, but they happen to be the same. So symmetrizing a symmetric matrix doesn't do anything. It just keeps it the same matrix. Okay. And this is another claim. And I think this might have been even an exercise in MATH7502-UQ. So look, when you do A times B transposed, you have B transposed times A transposed. And to see this, you need to just work out the matrix multiplication. Okay. Yeah. Okay. Now, let's actually use this to think about just inner product. So just because to review the inner product again, inner product for vectors U and V is U transposed V. You could take that to be the inner product, right? So now, some of you were troubled by the fact I took the transpose of the inner product and stayed with the same thing, right? So we did this in one of the computations last week. But if you do you treat now this inner product as matrix multiplication and take its transpose, okay? Now, I claim it's going to be the same thing because inner product is a scalar, okay? According to this rule above, what you're going to get is you're going to get V transposed times U transpose transpose. What's U transpose transpose? That's just U. Okay. So V transpose U is like U transpose V. Well, you could see this also by taking what the transpose is. Sorry, the inner product is. Not much here except for thinking that when you transpose an inner product, you actually didn't do anything. You did V transpose U, and that's like U transpose V, because you're just summing up the UI times VI, UI times VI, sum all those guys. So that's the inner product. Okay, and this is just a demonstration of what we said above. So I'm taking A and I'm adding it 3 element-wise. Not sure why that's needed here. Let's do A times B transpose, and let's do B transpose times A transpose, and we should get the same thing. Okay, so notice A times B transpose is B transpose times A transpose. All right, that was pretty much as we could say about transpose. I guess I didn't say here the transpose of an inverse. If A inverse exists, then A inverse transposed equals A transposed inverse. So we sometimes write A negative transpose to mean that. And that didn't work. So A inverse. So we sometimes write, where's my LaTeX mistake? So A inverse $1 here. Okay. So if the inverse of a matrix exists, we still didn't speak about when it exists and when not. We will in a few minutes, okay? If the inverse of a matrix exists, then when you do the inverse, because not all matrices have an inverse, okay? When you do the inverse of the transpose, that's like the transpose of the inverse, so you might as well just write A minus transpose. Okay. Transpose you can do on non-square matrices. Inverse, you only write that on square matrices. Okay. Determinants. Determinants. Questions? No. All right, so there's a whole bunch to do with determinants. We won't do it all, okay? So the determinant of a 2x2 matrix, there are different ways to define determinant. We won't even define it fully. I mean, we might revisit determinant in 2 weeks. I'm not even sure how much we'll do. We'll do it as we need. Okay, so determinants used to be a central part of linear algebra. Today, they're kind of a bit more on the side of linear algebra. Although, of course, we still need to know what a determinant is. Okay, so the determinant of a 2x2 matrix just multiplies the top left by the bottom right, subtracting the top right by the bottom left. Okay, so this is exactly what we did here. So the determinant of A, 1 times 4 minus 2 times 3, that's -2. And here I'm computing that the entries, you see 1, 1 times 2, 2, these diagonals, minus 1, 2 times 2, 1. Okay, you get the same thing. All right, so that's the determinant of a 2x2 matrix. Okay, a determinant is a number associated with a matrix. With any matrix? No, determinants are for square matrices. Okay, so here's B. B is non-square. It's a rectangular matrix. It's a chubby matrix. Okay, it's a fat matrix, 2 times 4. Take the determinant of B. Julia's mad. I do not know determinant of non-square matrix. Okay, just some things we just do for square matrices. Okay. The determinant of, what's this matrix that I'm highlighting here? What's this matrix that I'm highlighting here? The most common answer for today. It's I, thank you. So it's a 5 by 5 identity matrix, okay? And it's the determinant of the identity matrix just happens to be 1. So for next week, I'll actually suggest a 3 blue 1 video, 3 blue 1 brown video, which actually gives some meaning to what a determinant is. It actually has nice meaning when you think about linear transformations, about how volume changes. But we still haven't spoken about linear transformations fully. Look, if I take this matrix, diagonal 1, 2, 3, that's this matrix with 1, 2, 3 on the diagonal. Let's call this a matrix A now. Okay. So, and if I do the determinant of A, that of diagonal is product of the elements. Okay, so there's all these rules. Yeah, it's 1 times 2 times 3. So sometimes the determinant is hard to compute. For some matrices, it's easy. For example, for diagonal matrices, is that. Now, even if I now change A, let's put A in the coordinate 2, 3 to be negative 53, and A in the coordinate 1, 3 to be 7. It didn't like it. Why not? Oh, because A is diagonal. Funny. Interesting. So I have here a diagonal matrix A. I try to set its off diagonal entry. Julia is mad at me. Let's just do this. A equals. That's hard. Convert to a array of float. That probably won't work. 64 to A. Oh, okay. I'm so lucky I managed to do this. So the conversion. Oh, that's a great idea. Okay, let's actually do what Robert suggested. So before I explain this ugly thing, which I did here, let's go back to this A. And now we're slightly paying the price for a language that has types, okay? There's a lot of benefits, but it's kind of a bit harder, okay? So A, just like what Robert suggested, 0s 3, 3 plus A. Beautiful. Okay, and this is alternative. Alt is to use the convert function. Again, no linear algebra in this, okay? But this is how you cast, how you convert the type of A to actually be a matrix. Okay, so after we did that with A, let's now dirty A. And let's see what A is. Okay, so A is a diagonal matrix? No, it's not a diagonal matrix anymore. A is called, there's a name for it. I'll give you multiple choice. Upper triangular, lower triangular, or which one of those? Upper triangular or lower triangular? What do you think A is? It's upper triangular. Upper, even upper exclamation mark we had. Very good. Okay, so A is upper triangular. So the determinant of a triangular matrix is still the product of diagonals, okay, or triangular, upper or lower, okay? So, and a lot of linear algebra deals with trying to get kind of these nice matrices that are either upper triangular or lower triangular because they're much easier to work with. Kind of in a very rough analogy, it's kind of the difference between a tree and a general graph, okay? And that's if you've done any graph theory or something like that, if not, leave. Let's dirty A bit more. A31 equals a different number, okay? Let's see what A is. So now A doesn't have this nice structure anymore. It's not upper triangular, and we'll be extremely lucky if the determinant is actually going to be the product of the diagonals. It's not going to be anymore. Happens to be something completely different, okay? All right. Now, instead of actually giving the formula for a determinant, here is a function that computes a determinant of a general matrix A. Okay, we'll look at the implementation of this function in a second. The real juice is here. Okay, and for those of you that haven't programmed, this is if you are just now learning programming. I mean, all of you have programmed in one way or another, but if you kind of haven't done more, this is a typical recursion exercise. So this is my det. It's my implementation of a determinant. Okay, I didn't invent it. It's also yours at this point. So my det of A, first of all, we see it works, okay? So this was a built-in det that came in with linear algebra that's probably doing a much better thing than this. Not probably, for sure. This is a horrible implementation. Okay, it takes exponential time. Like if I do this on a big matrix, if I do my det on a matrix that's like 100 by 100, I might have to stop Julia. Oh, ran fast. 1,000 by 1,000. Now it's running. Okay, for a long time. Okay, so I'm going to stop Julia. Whereas if I do det on a 1,000 by 1,000 matrix, it uses much better algorithms. So in general, and there was numerical error. It gave us negative infinity. We already terminated. In general, this course doesn't deal with numerical algorithms, how to compute these things. It's also not so important, okay? Some aspects of numerical are important, and there's actually a course running now, and you might want to take it next year, numerical linear algebra, with a lot of data science applications. Okay, let's stop beating around the bush and look at this function. So how does this function work? Well, all the juice is in this. We'll get to this in a few minutes, or in a minute. This is some error checking. We get the size of A. If n equals m, we just never do this. That's this lazy or, okay? Which is, again, a short circuit or, okay? Otherwise, we say dimension mismatch. You can't do it if it's not a square matrix. Now, if it's a 2 by 2 matrix, then we do, 2 by 2 has simple formula. Okay. Higher dimension has a recursive formula. Okay. Now, you can read about this recursive formula because it's so not important. I'm not going to so much explain it, but here it is. Should be det or my det? Which one are you asking about? This? Oh, thank you. Thank you. Robert found a mistake here. My det. I mean, it can also work as det, but then my det. Oh, this is how it worked nicely for 100. Okay. So, okay, what I did here is I had a recursive call to well, it wasn't a recursive call. It was to det, which was the better determinant. But now I'll make a recursive call to mydet. Thank you. So this is like a function that you do if you're stranded on an island by yourself. This happens to people, by the way. And you have to write your determinant function. Yeah. Has anybody seen that movie with Tom Hanks when he had a Fred Wilson? What is it called? Tom Hanks with that Wilson, the volleyball. Tom Hanks, Castaway, right? So I don't think he wrote determinant in that. They cut that scene out, but you know, he would have done this and he would have done that. Okay, assuming he has a laptop. All right. And as I was saying, let's cut through this and do it. Expand one row and one column. Okay. So what we're doing here is we're taking the first row, okay, and we're taking the elements of the first row. And all the time we're multiplying either by a positive one or a negative one, a positive one or a negative one. Now, if I is 1, 1 plus 1 is 2, we get negative 1, 2, you get a positive. Then you get a negative. Then you get a positive, then you get a negative. I'll actually just put this down here. Basically, it's like positive, negative, positive, negative, positive, negative. You do this forever, okay? And when we do this, we multiply by this element, by that ith element, and then we compute the determinant of a smaller matrix, okay? Now, what's a smaller matrix? A smaller matrix excludes the first row, so its rows are from the second row to the nth row, okay? And it also excludes the ith column that you're working on. So here you're seeing a nice function called setDiff. SetDiff, okay? SetDiff takes a set of indices, 1, 2, 3, all the columns, and removes the singleton I, okay? That's like difference in sets, okay? So you remove that one element. So just so you see the SetDiff of, for example, 1, 4 from 3 would be the 1, 2, and 4. You see it removed the 3. Or if you remove the 2, it's 1, 3, and 4, etc. So this is a recursive call. Now, this is a recursive function because if you call it, say, on A that's 3 by 3, then it's going to call itself 3 times. And this is what you call the terminating condition because it's 2 by 2. Okay? And that's how it works. It's quite complicated. Let's do now again mydet of a 100 by 100. I think it'll be slower after I was corrected on this. Mydet of a 100 by 100. Okay, now we're speaking. Before, mydet cheated. It only did 100 subdeterminants of 99 by 99, which is called det. Okay, you see the point? Yeah. Okay, there's a lot happening. So of course this is a bad implementation, but it's good to at least see it. Okay, so that didn't work. If you do mydet 10 by 10, because there's like this recursion tree grows exponentially. It's like, you know, it worked, but it took a long while. Okay, relatively to a 10 by 10 determinant. If you take a random matrix, kind of a random matrix, and you compute its determinant, can it ever be 0? Like, or will it be 0 if I take, or is there any possibility? Is there a positive probability for it to be 0? Well, Jonathan says yes, but only because the numbers are kind of finite. You know, there's 64 bits, so you only have a finite number of numbers. But basically, if I do this, for example, I promise you, if I do now shift enter and this thing gives 0, I'm going to jump out the balcony. I promise. Okay, promise? No, it's not 0. So it's going to be 0 with 0 probability. And as Robert said, depends if your pseudo-random can include 0. Look, the pseudo-random, because what it's doing is it's making 4 random entries that are independent, the chance of the top left times the bottom right minus that times that to be 0 is actually 0. So what I'm saying is random matrices are not going to be 0. Okay? Of course, if I would do this, you know, let's take a matrix with entries negative 10 and 20. Okay? Well, the determinant wasn't 0, determinant wasn't 0, determinant wasn't 0, but now it was, okay? Because now it's the only kind of finite number of possibilities, right? Why am I telling you this? Well, so I'm saying any arbitrary random matrix that you choose won't have determinant 0. But in practice, many matrices have determinant 0 because they're kind of by design having determinant 0. Okay. So here's a determinant and my debt, etc. Okay, a claim which we won't prove now. The determinant of a product is a product of determinants. That's great because many things of the product are not the product of the thing, but it is for determinant. Okay, so I'm taking a random 4x4 matrix here. Where am I? Here. And another random 4, the determinant of A times B happens to be this thing. Did I run this? And no, the determinant of A times B happens to be this, and this is the other thing in this tuple is the determinant A times determinant B. Okay. Okay. So determinant of product is product of determinants. Claim, if A is invertible, then the determinant of the inverse is the reciprocal or the inverse of the determinant. Notice here, notice. On the left-hand side, I have A inverse. Okay, so that's an inverse matrix. On the right-hand side, I have a number inverse. So I could have written like that. So, Fadi, you asked at the start of the lecture what we mean by those types. Well, if it's a matrix, if it's a square matrix, then we mean determinant if it's clear in context. Okay, so that's what we mean. Sometimes mathematically you'll just write DET. Okay, but you can't, you know, that's the inverse of the determinant. How can we prove this one from this one? So how to prove what I'm highlighting now from the determinant of a product is a product of determinants. So how am I going to prove this? Let's do this. Let's go to next kind of quick little proof. So we have A, what we're saying is A inverse equals 1 on A if A inverse exists. Now, first of all, you need to get a bit mad here because you say, hey, what are you dividing by? Dividing, well, you don't need to, no need to get mad ever, but you know, you're dividing by the determinant. What if the determinant is 0? What if the determinant is 0? But if the determinant is 0, then the inverse actually doesn't exist, okay? And that's a one-on-one correspondence. Okay, we'll get to that in a second. Okay, now I'm getting things in the chat. Let's see. So Zay is saying let B equals A negative 1. Perfect. So what you're saying is let A times A negative 1 determinant. So that's what you meant by the B. This is like the B, okay? So we know that that's determinant of A times, whoops, times the determinant of A inverse. But what is this thing? What matrix is this? That is, now, most common answer for today, the identity matrix, okay? And what's the determinant of the identity matrix? What's the determinant of the identity matrix? 1, okay? It's not I, it's 1. 1 is like the identity matrix in scalars, okay? So that's 1, okay? So 1, the number 1 equals that number times that number, so now divide by that. So 1 over A inverse determinant equals, no, I should do this, divide by the other one. 1 minus A equals determinant of A inverse. Okay? That's it. That's the proof of it. So if you know the determinant of products or product of determinants, and you know what the determinant of an inverse is. Thank you. Good job, Zen. All right, let's get back to this. And Google Chrome. Okay, just make sure you can see it. Yeah. All right. Here you see determinant of inverse or 1 over determinant. Okay. Now look at this matrix A. What's its determinant? So I do 1 times 0 minus 0 times 1. Okay. So I'll put that A equals 1 times 0 minus 0 times 1, okay, and that's a 0, okay, the determinant is 0, and let's try to compute the inverse of A. I get the LA-PAC exception. Remember LA-PAC, the linear algebra pack, that's kind of this core linear algebra stuff that MATLAB uses and also Julia uses, etc. So this matrix is called, give me some names, some adjectives for the matrix A. Try not to be too offensive, please. Adjectives for the matrix A. A. What's a matrix A? Non-invertible. Other adjectives? Another one? Bad? Well, no, said no offensive. It's bad. Sometimes non-invertible is good, by the way. But okay. No, non-invertible. Not the nice one, but it's, is it singular? Singular, okay? So A is singular or non-invertible. Okay, these are synonyms, all right? Singular matrices have a determinant of zeros. Well, we're speaking about square matrices, obviously, okay? And they're non-invertible, okay? So that doesn't put us in trouble when we do this kind of determinant of the inverse, because we know A minus, if A is invertible. If A is invertible, we know that the determinant is not 0. Okay. When you look at the video of 3 blue, 1 brown of what a determinant means from a linear transformation, it actually makes a lot of sense to you. Now, let's look at this matrix. 1, 2, 3, 4, 5, 6, 5, 7, 9. Okay. What can you say about this third row? How did I get this third row? Look at the first 2 rows. How did I get the third row? How is the third row related to the first 2 rows? It's the sum of the first 2 rows, right? So it's a linear combination of the first 2 rows with weights of 1 and 1, right? Okay, row 1 plus 1 plus, thank you. So this matrix is also going to be singular, okay? So if I compute its determinant, I get kind of a 0, well, and almost 0, okay? A numerical 0. There's some numerical error, but this matrix is non-invertible. It's singular, okay? I could still compute the inverse here, and I think I'm all happy. I compute the inverse, but look, I get this horrible inverse. From a determinant of like 0, I get this infinity, like a bunch of infinities. This is what you call numerical trouble. In the end of this course, we'll learn about what's called the condition number of a matrix. And you see this number is like e to the 16. It's like a huge number. So this matrix is very ill-conditioned. Okay, it's mathematically, it's actually so if, by the way, look, if I compute my debt will be better than that. If I do my debt of B, we'll get a 0 exactly. And that's kind of nice because my debt actually did integer arithmetic and did not convert it to a floating point, okay? So did integer arithmetic, okay? So it's like exactly 0, even though the numerical debt gave it an almost 0. So we're not speaking about condition numbers yet. You can do a question mark on condition number, but it's towards the end of the course. Okay. Questions? All right. Inverse of a 2 by 2 matrix. Now, in general, this is special case of Kramer's rule, which we don't really speak about. Now, I'm sure some of you have studied Kramer's rule in some course in linear algebra. Okay, so there's like a formula for a general n by n matrix. You can do a formula for its inverse based on determinants. There's not a whole lot of use for it, but the 2 by 2 case is very important. Okay, now I did this actually last semester, but it's kind of like MATH7502 material still, but it's just so important. Let's just do it again, because it's also important, frankly, because it appears sometimes in quizzes and things like that, because it's like easy to work with a 2 by 2 matrix. Okay, so what I want to speak about here is inverse of A in R 2 by 2. I'm just using this occasion to introduce this notation. This is a notation of the 2 by 2. This is a space of 2 by 2 matrices, so A is an element of the space of 2 by 2 matrices. Okay. Okay, so a 2 by 2 matrix. So if A, let me write a different color. If A is the matrix A, B, C, D, so the A inverse is going to be this scalar, AD minus BC. What is this scalar here? What is this thing? It's a determinant, right? Thank you. This is just det of A. Okay, that's what this guy is. Let me write this in a different color, just so you see it's like a side comment. This is a det of A. Okay, or you could just write that if you want. Okay, multiplied by the matrix, and then what I do is I do dA. So notice D was here, bottom right. Now it's top left, and I do minus B minus C. Okay, minus B minus C. Okay. All right. So that's how you get the 2 by 2 matrix. Now, proof, I won't do the proof. I mean, first of all, this comes as like a special case of Kramer's rule. But what you can do at home, at home, you guys are already at home. So I cannot use at home in lectures. I need to say later, later. Well, maybe you're not at home. Anybody now like in a shopping center? No. Okay, so later, you're going to do A times A inverse. Try it, because it's just good exercise to kind of do equals the identity. So the way you would do it is you just say, I want to compute, for example, this entry. So I'm going to take this row of A times this column of A of this guy. Okay, and that would be the proof of this. Okay, just do it as an exercise later. You did it probably in MATH7502 before. So we have like this explicit formula for 2 by 2 matrices. There's also like a formula for 3 by 3 matrices and 4 by 4, but it's ugly. It's not useful. But for 2 by 2, it's useful, especially for pedagogical purposes or small examples. So many things are 2 by 2 matrices. Of course, in linear algebra, in data science, your matrices are big because you've got a lot of data. So here's a function that does this. This is still just kind of a bit of derive it. Well, okay, you do that. So we take the A. If it needs to be 2 by 2, so N needs to be 2 and M needs to be 2, you evaluate both these things. If not, then you say it's not a 2 by 2 matrices, okay? If you want to get this character, this Unicode character that looks like a nice multiplication, you do / times and hit a 10. Then you call this thing, this is called capital delta, okay? That'll be the determinant of A, okay? That's capital delta. And what I'm doing here is I'm checking that the matrix is non-singular. So I could have done, by the way, this is a mistake what I did. I should do abs of delta. Could have done delta not equal to 0. Okay, but you know, maybe it's so close that it's a machine precision number. So EPS gives you like a very, and you can do EPS on different types. It's like the smallest type, or it's like almost 0. Okay, machine precision 0. Okay, so I want delta to be strictly positive. It's important, this ABS, because the determinant can be negative. Determinant can be negative, and my matrix will be fine. Okay, matrix will be invertible, non-singular. Okay, determinant doesn't have to be positive. Okay, then I take A, B, C, D to be exactly these entries of the matrix, and then I just write out this formula, which we just did. Okay, so you flip the diagonal entries and you take minus of the others. I always forget which is which, but then I remind myself. I say, I try to remember. What am I going to do? Am I going to flip the diagonal and do minuses of the off diagonal, or am I going to do minuses of the diagonal and flip the off diagonals? But then I tell myself, for the identity matrix, what's the inverse of the identity matrix? Common answer today. You should have a special key for that. Well, you do have a common answer. What's the inverse of the identity matrix? It's identity. Thank you. Right? So you don't want to put a minus on the identity, right? So it has to be that the flipping is that. I'm just saying of a way to remember this, but it also kind of involves a bit of things. So if you test this, here's A, here's what I call A inverse, multiply inverse by A, you get that. No surprise. Okay, slightly boring. We'll get there. Okay, and this is what this EPS is. Okay, let's do something kind of completely different that you can actually make money with. No, I mean that you can work with. So the first application, K-means. Now, I actually think, can anybody tell me from MATH7502 students, if you actually remember that I did this in the first lecture last semester, clustering. So, yes, so I'm sorry, I will do it again. Okay, so this is like, yeah, K-means, right? So that's what we're going to do. Now, we spoke already about determinants and matrices, etc. The nice thing about this K-means is it's such a strong application of linear algebra that's really used in data science. I actually did a consulting project for a company, and what we used is basically K-means. But all you need for it is basically vectors and vector norms, pretty much. That's it. So it's not even using determinants. Okay, so that's kind of the first thing from this DSUC, data science use cases linear algebra. So if you click here, you go to clustering, and yeah, there's a Wikipedia link to that, but I also very much recommend looking at the VMLS book, Stephen Boyd's and his co-authored book, chapter 4, which is just dedicated to that. It's just a great simple explanation for K-means. Okay, so let's see what K-means is about. I'll actually start with this picture. Okay. So this picture is of, it's the one on the left, okay? And this comes from, this also comes from my book, from listing 912 and listing 913 of the Statistics with Julia book. Now, chapters 9 and 8 are not available in the online version, but I will put the drafts of them on Blackboard. I ask that you don't circulate these two chapters, chapters 8 and 9, because these ones we're not supposed to give out, but I am allowed to use them for this course, chapters 8 and 9. This book will go to the publisher soon. Okay, so there's like exact explanations of this. So this will be on by the end of the week. All right, so these pictures here, this is from a data set that's one of the most abused data set in introductory data science, and I'm shamelessly going to do so again. It's what's called the IRIS data set. Who's used or heard of the IRIS data set? In intro to data science, if you did it last semester, IRIS, like the flower, iris. Yeah, okay. So IRIS data. So basically you've got these kind of flowers, and they've got different species of flowers, and there's like this one variable is maybe the petal Petal is the leaf of the flower, the petal width, and the other one is maybe the petal height. So each point here is a vector, in this case of two-dimensional space, of a, ignore the red points, of petal leaf and petal height of a certain flower. But these flowers come from different species, okay? But let's assume we don't know the species, okay? So that makes this what you call an unsupervised problem. So we actually don't know that these guys, like you see on the right, are the red and the blue, the green. We don't know that. We just see these two variables. Now, in general, there's a conceptual thing here. A measurement of an individual is actually a vector. In this case, it's this point. It's a two-dimensional vector. Now, very soon, you're going to get to vectors that are 1,000-dimensional or 5,000-dimensional because each individual has like 5,000 data points. Okay, so that's what you'd call high-dimensional data. Okay, so a vector is a measurement, is an observation, is an individual. That's just a general thing kind of in data science, linear algebra. Okay, and in general in data science. Of course, when you're dealing with data, sometimes you have other things. You have some categorical variables, which means there's variables that are not numeric, okay? Or you've got other types of data that's not necessarily numeric, and that's not in the realm of the things that we're doing in this course. But the core of the things are after you took your data frame or your Panda and you convert it to data, it's in a sense, it's a collection of vectors. It's a matrix. It's something like that. Okay. So the clustering problem is an unsupervised learning problem where, again, ignore these red dots, okay? Where you're being asked, can you please find for me these different points and say which ones are similar, which look similar? Now, here the data is so clean that it's quite obvious. So you've got like one cluster here and one cluster there and one cluster there. You know, and maybe you don't know of this one that I'm highlighting here, this blue guy here. We don't know exactly who it belongs to. Certainly not this guy, we're not sure maybe if it's that to that. But most points we can kind of classify them and say they look the same. Of course, when you get to other data sets that are not as nice as this, sometimes the clustering doesn't look as nice, right? Now, exogenously, when you come to this problem, you can say, how many clusters do I want? Do I want 2? Do I want 3? Do I want 4? Do I want n? Now, again, with this two-dimensional vectors, it's not hard to see. I mean, you need to be a complete, I don't know, something to not think that there's 3 clusters here, okay? When you look at these blue guys, okay? Ignore the right-hand side when you look at the left, the blue guys, okay? But keep in mind that you'll be coming to 7-dimensional data, 20-dimensional data, 1,000-dimensional data. You won't know a priori how many clusters. So there are other ways of kind of choosing what kind of clustering is best. So that external choice of how many clusters is the K in the K-means. So K, I'm going to choose K equals 3 clusters, okay? I could have done this with 4 clusters. Well, we might see how this looks in a second, okay? So that's a problem. And then what we want is an algorithm that will just look at these things and say, these guys are similar, these are similar, these are similar. It won't say who is who because this is unsupervised, okay? That's the K-means. Other questions about, well, now we're going to have an algorithm for that, which is actually an approximate algorithm. It's a heuristic algorithm, but all it's based upon is norm and distance between points. Any questions? Okay. So just before the break, take a break in a minute. So there are 2 code listings here. So this first one, which came from listing 912 of the Statistics with Julia book, it actually uses the package clustering, okay? So it uses the package clustering.jl, you know, which is a package designed for clustering. Today, these packages are now being kind of meta-packaged in these other machine learning frameworks, okay? But this is a clustering jail, okay? Which does this K-means clustering plus other clustering, okay? And we're getting the data from a package called our datasets. Of course, on your computer, if you don't have these packages, you might want to do something like, you know, using pkg. I won't do it, and pkg.add our datasets. And similarly for the other packages. Okay, so that's the type of, if you don't have these packages. All right. And what we're doing here is we're actually using a closed box function, k-means. But then the next example, we're actually going to implement it ourselves and see how it works. And there's not more than just computing the norms, pretty much, and a bit of averages. Okay, so we take our second 10-minute break. And I'll be back in about 5 minutes to answer questions, but we start in 10 minutes from now. Okay, so enjoy the break. All right. Any questions? We'll start in 4 minutes. No questions? Xinyuan is asking if a diagonal matrix is a square matrix. Yes, when you say diagonal matrix, you mean a square matrix. We will actually use a matrix that has like a diagonal, but it's more fat or more skinny, but then you don't really call it the diagonal matrix, right? So diagonal matrix is a matrix with zeros only on the indices I equals, where I equals J, right? When like it's a diagonal. Yeah, you always mean it's square if you say that. It's a matter of terminology. Yeah. Great. So yeah, matrices have all these adjectives, all these things that describe them. Square, non-square, skinny, fat, diagonal, upper triangular, lower triangular, symmetric, singular, which is non-invertible, invertible, which is non-singular. Okay, and there'll be more. Orthogonal, we'll get to that. Okay, that'll be an important one. Diagonalizable, there'll even be a matrix called diagonalizable. And others. Full rank, non-full rank, all these things. We haven't done them all yet. Okay, so we're with clustering, right? So you got what clustering is about. Let me run this code and then explain how it works. But this one is just kind of stupid code because it just uses a package, and then we'll actually. So we'll first use it as users. Okay, this thing is still running. By the way, I hope it's going to run. So there's all these kind of issues. So it's using the clustering package. It's using the R datasets package. So that actually uses a whole bunch of datasets that exist in the R language, okay, such as this X-Clara iris dataset, okay, iris dataset. This is from Fisher. Fisher was one of the father of statistics back in the 1920s, 1930s, and that's kind of the dataset. This thing's apparently still running, okay? Maybe it's the first time, or I don't know. It's using random because what I'm doing here is I'm setting the seed simply because the algorithm actually is a randomized algorithm. So it uses some randomness. I'll show you how in a second. So this actually makes it run with the same way every time. Okay, so it's kind of just reproducible output. This measures package is not important. It's simply for using this margin and plots when you do two plots. Okay, margin needs measures. Okay, and plots is of course the plots, and I'm using the pyplot backend. Okay, so this is pyplot. You don't have to have this backend. You don't have to call this, but that kind of uses a pyplot backend. Okay, so that was all blah blah. Now here, this is a number of clusters, which is number of clusters. Okay, and this thing actually uses data set. This is from our data sets. Okay, from our data sets. And it creates this DF, which is what's called a data frame. So a data frame is like a matrix, but it's not really a matrix because it can have different things. Okay, I'll show you this DF once this thing finishes running, if it ever will. I think it's compiling this for the first time, or I don't know. And this now uses this convert function to actually make it like an array of numbers. So this is all organizing data. We'll look at the data in a few minutes, okay? Once this thing finishes running. Now, these are the two, this is actually the call to the package. Again, we're going to implement this in the next code listing, don't worry. But this is a call to the package. Now, what this is doing is, as a user, sometimes when you use an algorithm, you still need to know a thing or two of how it works. And this is how clustering works. So look at this image. Oh, now you can't even see the image. Okay. So the way clustering works is for every cluster, there's what's called a centroid. Okay. And a centroid is in a sense the center of mass. It's the average of all the points. Okay. So this is to init the centroids. So if I say that everybody belongs to a single cluster, all these points, then there'll be one vector, which is their center of mass. Now, how do I compute this vector? Basically, I'll write this above while this thing is still running, and I start to pray to God that it'll ever finish. So if I have like vectors that have, I'll just write like this. I'm just writing in some messy way. So they have coordinates. Oh, I see. Let me write it as a LaTeX formula. So if they have coordinates x1 and x2, this is one vector. Okay. And this is another vector, y1, y2. Okay, I'm writing them here as row vectors, but it doesn't matter. Okay, so if, for example, I would do this, then what I've done is I've averaged the first coordinate of them, the x coordinate, the x1 plus y1 and x2 plus y2. So think of these two vectors, the vector x and the vector y in space. I've actually found their midpoint. Now, I could have added here, oh, I see this thing finished. I could have added more vectors. I'll just do it with like a third one, z1 and z2. Okay. And then I'll divide by 3. So this is basically, I'm averaging the one coordinate over the vector x, the vector y, the vector z. I'm averaging the two coordinate over x, vector y, vector z. Okay. So this will find the center point of 3 vectors. This is what you call centroids. So the clustering, let's look at the result of the clustering here. Let's look here for a second at the one on the right, okay? So there is some point here in the center of the blue, which is the centroid of this cluster, okay? By the way, sometimes you actually care for that point when you run clustering because you would treat that point as like the typical blue point, okay? And there is some point here, which is the center of the green, and there is some point which is the center of the red. Now, when you initialize the algorithm, you still don't know who is blue, who is red, who is green, right? They're all monochrome. They're all the same color. So what we're going to do is we're actually going to guess that the centroids are those 3 initial red points. So that's what this init seeds did, okay? Let me run this again so you know, at least let's hope it runs fast. Probably will run very fast, or maybe by the 3rd time it'll be super fast. Now, here, this k-means function in line 9, this is where the beef. This is the action. Okay, so it takes data. I see this is still running very slow. I'm very disappointed. I don't know why. Okay, it takes data and it asks, please compute for me k clusters, and the init point will be these seeds, those random seeds. Okay, okay, 3rd time is going to be faster. Right now, let's run it. Come on, now it's going to be super fast. Yeah, okay, now it's fast. Yeah, 3rd time. So you see, Julia's kind of takes a while to start. Okay. Just to see some things here. So look at DF. This is now completely doesn't have to do with linear algebra, but as a data scientist, see this. So I do DF enter. This type of thing is a data frame. You see, it's kind of like an Excel spreadsheet. Okay, this is a data frame. That's DF, and you've got the V1, V2. And of course, we don't use this. We then convert it here to data. Look at data. And data is now just a set of 3,000 points, okay? So a set of 3,000 points of V1, V2. So these are the 3,000 points that you see here. All right, so this is the end of the algorithm. And the number of clusters, I apply the n clusters function on this x clara means is like the result of this k-means. Let me actually do that too, so you see what that is. It's probably a structure which is like the result of, you know, it's of a type k-means result. So it's a structure that has a whole bunch of things, and I can query it, not like you would do in Python with a dot something, because Julia is not object-oriented like that, but I rather apply the n clusters function to it. So we had 3 clusters, okay? We asked for 3 clusters. And then the counts are the number of elements in each cluster, which is kind of uniform. Just to see how this works, let's just put here a 2. Something in the graphics might break if I change this 2. I'm not sure, but okay. So maybe it didn't break. So look, this is how you would cluster it with 2 clusters, okay? Of course, this is unnatural, but maybe you didn't know ahead of time, okay? And let me put 4 clusters. It's also unnatural for this. This is how you'd, oh, okay, it's not doing the 4th color. It's circling through the color. With 4 clusters, I need to kind of, need to do another plot here. I will do it just so you see it. For the 4th group, the color say black. Okay, so this is how we would do it with 4 clusters. Also unnatural. Okay, for this is very synthetic data. It's natural to do it with 3 clusters. All I'm saying, I'll put this in comment, right? 4 clusters. But we'll do it with 3. Okay, so this is how you use this as a user. Okay, and then you can kind of take these points and you can say they're similar, or these are now, if these are customers and you're a marketing manager, right? You'd say all these customers that were clustered in group 1 are similar, so I'll spam them with that. And all the ones in green are similar, so I'll spam them with that. Again, think of the points will be in high dimensional space. Okay, questions? No? That would, okay. So now how does this thing work? How does clustering work? Well, there's basically just a few equations to consider, and I put them here. And again, you can look at chapter 4 of the MLS. And this equation here, this guy, is the clustering objective. Clustering objective. Let me actually see if I might actually even scratch on it so I can, you could see my annotation on it, I assume. Okay, this thing I've put around is a clustering objective. I'm doing this on the computer, not on the iPad. I hope you can see this red thing around the objective. So what's an objective? What does the word objective mean? Objective. So can you see this red? Just to know, because I'll do some more scratching. Yes, thanks. Okay, so so many algorithms in data science and machine learning are, in a sense, optimization algorithms. So in a sense, even though you're trying to find the optimum, the best point, and that best point is kind of the best point that maybe describes your data the best. That's often the case. So the way we can do the clustering objective is we can say, well, let's hope for a clustering result that does the following. It does the following. What we're going to do is we're going to set, if we have k equals to 3, we had k groups. I'm now writing on the computer, so it's a bit messy. So if we had k equals to 3, then what I'm going to do is for each, the way the clustering result looks, I'm going to look at my data points x1 through xn. Now, just not to confuse you, before I had x1 and x2, and these were coordinates. These were coordinates of a vector. Now, each one of these guys is a vector. This is a vector. And the second one is a vector. Oops. And the nth one, the last one, is a vector. So I've got n data points. It's very hard for me to draw here, sorry. I've got n vectors, okay? I've got n vectors. Now, the way the clustering result works is what I'm going to do is I'm going to put, I'll have like the index, the group which I associated with them will be like C1 is the class of the first one, and C2 is a class of the second one, up to Cn, okay? So these C's, you know, Ci is just an element of the set 1, 2, 3. Or 1, 2, up to k, but I just have 3, so k equals 3, okay? Now, when I do these sets, I'm actually then going to have 3 centers of mass, okay? 3 centers of mass. So the centers of mass are going to be Z1. That's the center of mass of the first cluster. Z2. That's the center of mass of the second cluster. And Z3, that's the center of mass of the third cluster. Okay? These are going to be the 3 centers of mass. So the way I'm going to compute, for example, when I'm going to compute Z2, what I'm going to do is I'm going to do the Z2 is exactly going to be this guy. Okay? Or Zj, this is for j equaling 1 and 2 and 3. I'm going to divide by the total. This G sub j is the set of indices that are of cluster J. So I'll actually write this. I'll write G sub j is a set. It's all of the indices I, such that, this is now using kind of set notation that appeared in MATH7501, etc. Not critical if you don't do this, such that Ci equals J, okay? So, you know, there's 2 ways to kind of describe the clustering. It's the set of the indices, okay? That's the G, or it's the actual flags, all right? Now, what is this? What is this? So we started the lecture with kind of Fadi asking about these bars. What do these bars mean? What do these bars mean? The ones I'm kind of doing here. Around the set, the bars around the set. They're the cardinality, thank you. So they're the number of elements in this set. So what we're doing here is exactly doing the average of all the elements of that set to find the center of mass. This is what we call the centroids, okay, the center of mass. Okay. Now, that's it. So given if you knew the clusters, you know how to find the centroids. Now the clustering objective, what you would like to do is basically, you would like to assign those C's such that this whole thing, which I put in red here, this thing in first, is minimized. You would love to be able to minimize it, okay? So, but it requires this kind of complicated thing. How do you, assign clusters? How do you assign observations to clusters, right? So let's look what are the elements here. So this here, we actually didn't, this thing I'm doing here, somebody else drawing on the screen. Okay, maybe. So this thing here is the norm of a difference of two vectors. So we know what the norm of a vector is. We spoke about this, but we actually didn't speak about the norm of the difference of two vectors. What would you call that? The norm of the difference of two vectors. I'm actually going to put this in the chat. I'm going to put norm of u minus v. I'm not going to put a square. What would you call this? Norm of u. What would be a word? What I just put in the chat. Norm of u minus v. The distance. It's a Euclidean distance between the two vectors. Very good, thank you. So that's a distance between the two vectors, okay? And we're going to look at the distance squared because it's easier kind of to work with squares. Okay, so we're going to look at the distance squared. So we would want the first coordinate to be close to its centroid, the second one to be close to its centroid, up to the nth one to be close to its centroid, and we want this distance square minimized, okay? We would love to be able to optimize this. However, optimizing this is computationally infeasible. So many things in data science are kind of to do the best optimum is computationally infeasible. So what we're going to do in clustering, we're going to take a two-step approach. We're going to alternate between two things. We'll start and we'll assume, we'll assume we know our centroids. Okay, we'll know the centroids. And then, let me now clear all this mess here. Zoom out. So we'll assume we know the centroids. So we'll say fixed, I use the word centroids, you can also call them the representatives. We'll have fixed representatives. And then with fixed representatives, if I know my representative fixed, what I'm going to do is I'm just going to say, okay, who is closest to the first representative? And I'll color them, they'll be type 1. Who is closest to the second representative? They'll be type 2. Who is closest to the third representative? They'll be type 3. Just to, if you want to kind of see visually how that would work. So like this is like the first iteration. So I'll say this representative, right? So I'm gonna now select all the points. Clearly, I mean, these points are close to it. These ones, probably like all the points here and maybe like here, all these points roughly, I'm kind of rough, are closest to this guy. So then I'm gonna say these are all of that type, of type 1. Next, I'm going to look at the second representative. Let's put it like this one. I'll say, what are the points close to that? So maybe it's like these. Okay, I'm kind of encircling these points. And then I'll say who is closest to the third representative. That wasn't all these points, okay? Each point should be closest to somebody. That's not a complicated operation because I need to run per point and I need to see which one of the three representatives is closest to it, assign. Which one of the three closest assigned? Which one's three is assigned? So at this point, I've got these three clusters that I drew now. Now what do I do? Given that these are the points, then it's not hard to compute their center of mass. Like the center of mass of this one is no longer going to be, of this red one here, is no longer going to be this point. It's going to be maybe roughly here, okay? Because it's taking the mass which is combining these two. Center mass of the green is going to be here, and center mass of the blue will be elsewhere. So I run with a few iterations like this alternating. It's an alternating algorithm between these two steps. The linear algebra here is minimal. It's just norms and averaging, okay? So, but it's important because you can represent points as norms and it's an extremely powerful algorithm. So then I fix the representatives and I fix the assignments. I fix the representative, fix the assignments. I alternate between these two guys and that's how I get my clustering. Okay, that's k-means clustering. You could read about it more in VMLS, in the chapter 4 of VMLS. VMLS, just in case you kind of have not connected to that. So that's this book, VMLS, this one. Vectors, matrices, and least squares. Okay. And you can read about it elsewhere, but the VMLS description is great. So let's see now a simple implementation that just does it, doesn't use the package, but just does it from first principles. So all I said is unpacked in just a few lines here. Let's run this. And as it runs, let's describe. So again, it's pre-compiling, blah, blah, blah. Let me explain line by line. Any questions? Okay. So our data sets, distributions. The distributions package allows us to use distributions. I'm not sure how we're using, because we're using uniform distribution here. It's not critical. Okay. Random linear algebra, etc. 3 clusters, data size, n is the number of data points, okay? This data frame you see in Julia, even though it's not object-oriented, the size function has multiple methods, and you're now applying the size method on the data frame, so you're getting the number of rows, number of columns. We don't care for that number of columns. Then data points converts, these are, the data points is now of a different order. Of a different type. So data points, I think here it's easier to work here as an array of arrays. Okay, so this is like the first, you see it's an array of arrays. Okay, so this is the first data point, this is the first vector, this is the second data point, the second one, there's 3,000 of them. All right, that's data points. What does shuffle exclamation mark do? Take a wild guess. Shuffles, okay? It's often when you come to data, you actually want to shuffle it to not have some original bias that depends on how the data was organized initially in the data frame. Okay, it never hurts. Okay. What we do here is nothing big. We just basically finding just the minimum x and the maximum x and the minimum y and the maximum y. This one is tailored for 2-dimensional data. Okay. Again, there are multiple variables at play. There's how many data points you have. There's what's the dimension of each data point, and there's how many clusters you have. Okay, these are kind of 3 different dimension parameters. Okay, so we have 3,000 data points, 2-dimensional data, and of course you got to think 20-dimensional data or 100-dimensional data or 1,000,000-dimensional data. No joking, no joking. Okay, or in 3 clusters. Okay, so but this is tailored to 2-dimensional data. Okay. Now, the means are another name for these representative, these centroids, etc. So these are going to be data points that are uniform. This is how you can get a uniform value between y min and y max. Okay, that's why we use the distributions. I mean, that's not critical. So it's just within this bounding box where the data lives, it's going to select 3 random points. A much better way to select the means initially, like this is the initialization, is just to select 3 arbitrary points as a means, as a representatives. Okay, so you could have selected a point as a representative. The label is a very common word in data science and machine learning. Labels is what you assign to the cluster. Are you of type 1? Are you of type 2? Are you of type 3? Okay, and prev means minus the means, so this is to not stop immediately. Now, the way this algorithm works is it says, what's going to happen, by the way, with the clustering algorithm? Some algorithms in machine learning, they go on forever, like an infinite sequence, going forever, and error becomes smaller and smaller and smaller. What's going to happen in a clustering algorithm? After a certain point, things will stop moving. Okay, that's what's going to happen. But still, the stopping criteria here is that the distance between the previous means and the current means is less than or equal than this threshold. Okay, so that's a stopping criteria. You could have done a different stopping criteria. And then we just remember what the previous means were. I mean, that's the only reason why the previous means are used. So where is the meat of this algorithm? It's simply in these 2 lines, simply in these 2 lines. That's all there is to clustering. Okay, so let's see. How does the first line work? The first line reassigns the labels, okay? And it says, the labels is going to be a comprehension where you're going to run for all the x and the data points, the 3,000 data points, okay? Now, for each data point, you've got this inner comprehension. Okay. You might think that I'm just explaining code here, but no, this is actually the algorithm. Okay, so look, I'm just opening it up so it's a bit more readable like this. Okay, so this inner comprehension is going to take the norm between the means I is just going to be 1, 2, or 3, and x. Okay. So this is just going to be an array. What's going to be the length of this array when I run this? Those things that are highlighted. What's the length of this array? 3. It's just an array of length 3, thank you, which says how far is point x from this mean? How far is point x from this mean? How far is point x from this mean? And the argmin is going to be the index which is minimal here, okay? argmin, I'll write it in the chat just so you see, argmin, you see there's a difference. The min is a minimizer, the argmin is the index that minimizes. If you used in Julia, I'll write in the chat again, if you would have done find min, it would give you both a min and argmin, but argmin is good. Okay, so this is how you reassign the labels. Very simple. So you've now did the reassignment of the labels. Once you reassign the labels, well, now let's just compute the means. So how do we compute the means? In the denominator, we have a count. This thing that I've highlighted is the count of how many labels are now of type I. Okay, because I've just reassigned, so the number of labels changed. Okay, maybe it's 3,000, maybe it's, well, we don't want it to be 0 or the algorithm will crash. Okay, this is not such a robust algorithm. If you might divide here by 0 if something's very bad, it's not good. But let's hope we're not dividing by 0. Okay, and so this is not a super robust implementation. Okay, it's unlikely that the number of labels of I would be 0, but maybe if you have many high dimensional data at different points, and k is maybe a bigger number, etc. And here you're summing. This is how you can select this thing I've highlighted here. This is a selection of the data points for which labels is I. Okay, so these are all of the data points of that label. Okay, that's it. That's the means. So labels means, labels means, label means. Let's do print then. Next, run this. Let's see how many next. It didn't do too many next. Look, it only did like 10 iterations or something. And that's it. At this point, I have the labels, okay? I have the labels. So if I want the array of labels, you know, this is the array of the labels. I could plot them again. I won't do that now, okay? And we want to count how many labels are of a specific type. And then we get 899, 1149, 952 with a manual implementation, which should agree with this implementation. Okay. It doesn't have to be because the initialization could have been different, but it happens to agree. Questions? That's clustering for us. No? Oh, okay, so yeah, so labels, if I do labels equals 3, it'll get mad because I cannot compare the scalar 3 to, well, it'll go mad twice. Labels equals 3, I cannot, Okay, so what I did here is, I mean, you can always say, look, the array 1, 2, 3, does that equals 8? No, it doesn't, okay, but because it's a different thing, but it's not doing element-wise computation because these are different things. So the dot equals 3 broadcasts comparison to the scalar 3 of labels, and then I get an array of booleans. Okay, I get an array of booleans. That's this dot equals. More questions? What are the common applications of k-means? So this falls within supervised learning, and it's extremely important. It's extremely important to often. So this one consulting job I did was when you're looking at customer data and you put a customer not as a 2-dimensional vector, but as like a 40-dimensional vector, and you want the marketing manager that then deals with the customers to actually know what is a typical customer of a different type. Okay, so you want to kind of, instead of thinking of the customers like the 20,000 customers that you have, okay, and you have data on the customers, poor customers, okay, so what you want to do is you want to group them into 5 groups or 6 groups. You can sometimes call it in software design and also in marketing personas. What are the personas? So then you find kind of your groups of customers. And you even later care for the centroids because they're like the typical customers. So that's one application. Now, other applications, you'll actually see that k-means is sometimes you're kind of pre-processing the data before you're doing something else. Now, there are more robust clustering algorithms than others, etc. But you know, this is often good enough. If you look at the VMLS book, they actually have great things because they do clustering with Wikipedia data, and they do clustering with digit images, which we'll work with here, etc. Now the question here is by Hideki is how to decide the number k. So often you come to a machine learning algorithm or a data science algorithm, and k, you have some hyperparameter. It's called some hyperparameter. Here, obviously, we know that the k is kind of good as 3. You just look at it. But unfortunately, you can't look at 20-dimensional data easily. Okay? So what you can do is you can do parameter tuning, and you would kind of plot, for example, this loss function. You call it a loss function because it's like, you know, if this function was 0, you're like with 0 loss. You love it. You love it. If this was 0, everybody's on their centroid, right? But this function is only going to be positive. So you might plot this function for k equals 3. You'll plot it for this guy I'm highlighting here. You'll plot it for k equals 4, for k equals 5, for k equals 6. And you'll see kind of the more, as you increase k, your loss will decrease, 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 because you're actually allowing more and more granularity, right? Now, yeah, again, if you had k 100, then if you had k 3000, if I would run clustering with k 3000, each point would be an individual cluster. But what you're often looking for in such a function is the knee. You're saying, okay, if I add more clusters, suddenly the loss stops diminishing, and then I find this knee. There's not an exact science on how to do this, but that's plotting your loss in terms of the hyperparameter. Okay. Yeah, the elbow method, the knee, the elbow, the ankle, the nose, I'm not sure. Yeah, one of those. Other questions? All right, let's get back to linear algebra. So that was like one of 12. One of 12 data science use cases. Next one is convergence of the perceptron, which actually only also just relies on inner products and norms. Okay, and we might do this in a week or two. Maybe in 2, maybe after your quiz, or maybe just minimally, because some of these you'll kind of investigate more yourself. I'll just speak a bit and you'll do it more as part of your project. Okay, and then the next one, least squares data fitting, is a huge thing. This is like the thing that drives the world. Okay, but we have a bit to go until we get to least squares. All right, unit 2. So we're now I'm moving on to what's called, we're in this guy, Clouch, core linear algebra with Julia. So I guess I put gradient vectors here, but that's well, it's appearing in the unit 2. Okay, so we're pretty much going to unit 2. So this unit 2. Let me restart the kernel. Let me close this one, and you can go to running and kill this. Let me actually shut down both these kernels. You can do it, computer. Shut yourself down, and then I'll start again. Okay. So what we have here is Gaussian elimination, solving equations, and pivot and rank, and a bit of LU factorization, and then something different, which is Taylor series with Jacobians. So we'll get to a lot of this next week, and not today. I might actually jump almost directly to Taylor series quite soon. But I'm just going to start with linear equations, and then we do the rest of that next week. So it's kind of in one go. Now there's a question: is that finding the weights of the neural network for perceptron? Yeah. So the question by Rob. So the perceptron is like a very early neural network. It's kind of like a single neuron in a sense. And what we can do, it has an iterative algorithm, and we can prove that this algorithm converges. That's the second thing. Okay. So sometimes what we're going to do is not focus exactly on the algorithm. And the perceptron is not really a useful algorithm anymore. It's kind of part of something else, right? So you've got SVM, support vector machines, and neural networks, etc. But the convergence proof is kind of nice. Okay, so linear equations. Most of you have done this, almost all of you in one form or another. And some of you that have done a linear algebra course might think that, might have thought in the middle or towards the end of the course that most of linear algebra is just doing this kind of Gaussian elimination. Has anybody sat in an exam and had to do Gaussian elimination before in your life? I'm sure some of you have. Yes. Oh, condolences. Okay, years ago. Yes. Well, not going to happen again. 2020, you study from home, but no, you don't need to eliminate in an exam. And we'll actually learn how to solve linear equations also using QR factorization as opposed to using the Gaussian elimination. But let's speak about it very briefly, okay? Also for a matter of review, and then more next week. Also for understanding the LU decomposition. So here now, X and Y, in this guy, they're scalars, okay? So this is two equations, two unknowns, okay? Two lines, right? Two lines. It can be that the lines are the same lines. It can be that the lines are parallel, okay? And most probably the lines just intersect, okay? All right. You can represent the system as follows. All right. So linear equations can be represented as the matrix A times, now I'll use notation and I'll call the vector X. The vector X has a little X in it, okay? As the vector X is XY. That's a vector X equals the right-hand side. What letter do we use for right-hand side? Which one do you like? Typically it's like a B. AX equals B, okay? So many things in life can be positioned as AX equals B. Okay? AX equals B, linear equation. So how do we solve these linear equations? Of course, you know, there was like in high school, you had the method of substitution, etc. But the more standard way is to actually modify the equations and then subtract them, okay? So what we're going to do is we're going to multiply the first equation. We're going to look at what our goal is to make this thing here a 0. Okay, we would like to make this thing a 0. All right, so we're going to multiply the first equation by 3. Okay, we'll multiply the first equation by 3, because then we'll have here a 3, and we'll have here whatever, a -6, and we'll have here a 3 again. Okay, that's what happens. Okay, when you multiply, you can always do something to both sides of the equation. Okay, that's kind of the idea. Okay, the equation stays the same. Well, you can multiply. Okay, and then we're going to subtract. Then we're going to subtract. So if we do this, so you take this row 1, -2, you multiply it by 3 and subtract. So 1 times 3 is 3, minus 3, you get here a nothing. By this nothing, we mean a big 0. Okay, there's a 0 here. There's a 0 plus this. Now you had 3 times -2, which is -6. So 2 minus -6. Did I do this correctly? Multiplied by 3 is an 8. This is a mistake. Mistake here. This is an 8. Missing an 8. Right? Correct me if I'm wrong. 8. Okay. And yeah, -8. I think 8. So 2 -6 is an 8. Yeah, I think it's an 8. Okay. Stop me if I'm wrong. Unless I make a mistake, tell me. And then you have a 3. Oh, what did I do here? So, oh, that's an 11, right? So 3 times a 1 minus this is an 8. I think we're okay. All right. Again, stop me if I made a mistake. I think so. All right. So this is how we do it. Now, what do you call the matrix A? What adjective would you say for the matrix A? How do you call the matrix A? Upper diagonal. Thank you. Now, we like upper diagonal because now, then this equation here, this guy is easy, because then you can read off. So you know that y equals 1. That's again a mistake, sorry. So bad at this. Y equals 1. Okay. So y equals 1. And from this we can find the x. Okay, how can we find the x? So if y equals 1, then you've got the equation, just to see this here, from y equals 1, then you've got now the equation 1x minus 2 times the y, which was defined as a 1, equals a 1, right? That's the first equation. Okay, so then x equals 3. Okay, so x equals 3. Okay. So what we found is that the solution is solution is 3, 1. Let me put a transpose just so, because sometimes you write the vector like this, 3, 1 transpose, but it's actually the column xy. Okay, 3, 1. Let's actually see this. This is A, this is B. 1, -2, 3, 2 times B, 1, 1. Let's do that. A times 3, 1. Is 111, right? So we see that A times 3, 1, does that equal the B? Yes, it should be true. Okay, well, 1, 1, or I could have just done that. It's true. Okay, or alternatively, I could have done A times 3, 1, that's a solution, minus B, and that should be a 0. Okay, great. And here it is, just if you want. So this is now doing it. This is how you doing the row operation manually. Okay? So what we're doing now is we're taking A2, which would be a copy of A, and we're saying the second row, that's the thing I'm highlighting, the second row is what it was before, minus 3 times the first row. Okay, and that's what you get here. Okay. Is that correct? Yes. Yes. Okay. Oh, and here is the solution. Okay, that's what we did. All right, great. Now, the Gaussian elimination algorithm can continue and do this. And the way you do it in Gaussian elimination is you try to eliminate row after row after row after row after row, and you get done with your first row. Then you'll go to the first, element. What I want to say is if you have a matrix, I'll draw it a second. So if you had a we'll do it a bit more next week. So you had a matrix here. I'd want to keep this value here, and I'd want to zero out this, and zero out this, and zero out this, and zero out this. And once I'm done, I want to go to the next one, and I want to keep this entry here. And I want to zero out this, and zero out this, and zero out this. Okay, these are like entries. So these entries which I'm not zeroing out, if everything works, they're called the pivots. Okay, they're called the pivots, and we'll speak about it much more next week. Okay, so that's how Gaussian elimination works in general. But let's just see a few more general things before getting kind of in the full details of Gaussian elimination. Let's just consider the system of equations again. All right. So first of all, this is how you would solve it. Solving using the backslash operator. So this is how you'd solve it with using the real power of a linear algebra solver. Okay, so the backslash operator takes for you, I could have done, let me just also do B equals 111, and I could have done just A backslash B. Okay, just if you want to see this really works for a big thing, look, let me take the matrix, say it's going to be 1,000 by 1,000. Let's take B to be a vector of a random vector of 1,000. Okay, so this is big stuff. Now let's do X sol is A backslash B. Okay, and let's do, and it's solved now a system of 1,000 by 1,000. Okay, 1,000 equations is 1,000 unknowns, and let's now do A times X sol minus B. And we get all zeros. Well, how do we want to, how will we check that this is all zeros? Let's actually, well, let's compute the norm of this. Okay. Norm not defined. Why is norm not defined? Let's do using linear algebra. Okay, and you see that you solve the system of equations. Okay, so you can even do the help of this backslash. Help of backslash is they call it the backslash operator. Now, it turns out that this backslash operator actually does so many things. So even if you had more equations than unknowns, it'll still do things for you. It'll find least squares, which we're going to learn a whole bunch about. Okay. Okay. Thanks, Robert. Okay. So that's how you can solve it like this. Now, here's how you can solve it inefficiently. So remember, we had the system of equations was ax equals b. Okay, ax equals b, so many things in life are ax equals b. All right. So what you're going to do is, how do you solve this with an inverse? You left multiply, okay? Left multiply. When you multiply by a matrix, you can't just say multiply. You need to say right multiply or left multiply. Huh? Not okay just to multiply. Okay. Can you write multiply by A inverse, by the way? I'm saying left multiply by A inverse. Can I write multiply by A inverse? Can I even do this in terms of dimension? So B is a column. Can I write multiply by A inverse? No, I cannot, because I cannot take a column B times a matrix. I can only do a row times a matrix. Okay, so if I left multiply by A inverse this, A inverse times A becomes I, so to get Ix equals A inverse B, or X equals A. Okay, so that's how you do it. So you can always take your B, this is my B here, and multiply it by the inverse. No, this is the wrong A here. Let's go back to the original good A. Bad A. Let's take the good A and good B. This is like 1,000 by 1,000. Okay, we'll finish in a minute. Okay. But this is typically not the way to do it. So you don't compute an inverse and multiply by the right-hand side, because the Gaussian elimination carried out using the backslash operator is much more efficient. Actually, the backslash operator did much more than just Gaussian elimination. It really did it in the most efficient way. Okay. All right. So this is solving equations and unknowns, and of course there's more. So some bad things can happen. Okay. What are the bad things that can happen? Let's just, before we leave, let's consider. Let me put this system of equations for you. Okay, take this one and copy this matrix here. This is how I can do. This is one way of doing matrices in MATH. Okay, and let's just see this. What we're going to speak about next week is all the bad things that can happen. Okay, so I'm going to put this system of equations: 2x minus what's the problem here with this system of equations? Cancel. Linearly dependent. Okay, linear combination. Okay, all those things, exactly. So that's a case where if I would compute now the determinant of the matrix A, which is 1, the matrix 1, -2, 2, -4, then the matrix A is singular. Okay. And there are other cases, right? I could have had a system of equations. Just I'll do one more and we finish. I could have had a system of equations which is like this. Let me do. Oh, okay. Let's actually make this good. But let's add here another equation. This is a LaTeX way of writing these tables. Okay, there are different ways of doing it. So I think. Oh. Okay. So is this thing going to be solvable? I mean, when you have 3 equations and 2 unknowns? I mean, you can have cases with 3 equations, 2 unknowns that are solvable if that are exactly solvable if one equation is a consequence of another. But in general, not. And this is a beautiful case where we'd want something called least squares, right? Robert says overdeterminant, right? Exactly. Okay, and Zhang says no, right? And we'll deal with such cases as well. All right, so I think that finishes off today. What you're going to get is you're going to get homework 1 very soon, tomorrow or the next day, and you've got a tutorial, which is basically the tutorial this week is again with Sam and Walla. Those who didn't meet Walla because you're probably abroad, she was walking between people and helping, but she might also help with the chat, okay? And that tutorial will all be about just getting in tune with linear algebra functions in Julia, even though you might not understand the full linear algebra yet. Are there any questions? Okay. So everybody, thank you. Have a good afternoon if you're in a different time zone, or a good night. Okay. Bye-bye.